A newly proposed mathematical construction, known as a stabiliser Ewens deformation, constructs a complex family of Markov chains operating directly on binary strings. This animated equation marks a mathematically precise boundary. It is the exact constant, log 2 over 2 delta, times n over log n, where a sharp stationary average chi-square transition occurs. Reaching that constant presents a paradox. Looking only at the count of ones inside these binary strings, the system collapses into a highly simplified process operating on a straightforward n+1 state space, producing the complete two-parameter Hahn spectrum. This split screen compares that mathematical simplification on the left against the operational reality of the chain on the right. The actual labeled binary words span a massive 2 to the n state space. To understand exactly why the transition occurs on the n over log n scale, we will track this construction entirely from its stationary law, through the full word spectrum to the final asymptotic threshold. The boundary of this mathematical claim is strict. The result applies exclusively to an explicitly defined stationary average trace observable. It does not describe worst case, typical start, fixed start, or total variation cutoff theorems. Because the count and word chains share an absolute spectral radius, but do not share spectral multiplicities, the full word mixing theorem cannot be derived as a simple corollary of the count spectrum. We have to map the full space. The construction begins with an algorithm processing discrete nodes via random permutation, rearranging them into these mathematical cycles. Each cycle receives a new binary label from two distinct blocks. These operate under completely different Ewens parameters, denoted as alpha and beta. To maintain equilibrium in the system, the probabilities governing this cycle coloring process are strictly constrained by detailed balance. As a result, the count of ones across the chain settles into a precise beta-binomial stationary distribution. By applying a unique source-blind specialization, the model strips away the explicit dependency on those two initial source colors. That specialization directly generates the complete two-parameter Hahn family on the simplified count process. While this asymmetric construction solves the count process efficiently, it obscures the vast majority of the 2 to the n state space. Exposing that underlying structure requires a latent beta update. Isolating a single node, the latent beta update shatters it vertically, revealing parallel planes of binary word structures. Within this expanded space, polynomial functions are filtered by square-free degree, perfectly isolating mutually orthogonal intrinsic degree layers labeled as L. These isolated degree layers are mathematically self-adjoint, setting up a clean basis for spectral analysis. This yields an exact eigenvalue formula for degree L, but it carries a massive binomial multiplicity weight of n choose L. Here, the variables u and v are beta distributions derived directly from the earlier stabiliser cycle construction. If distinct degrees happen to share the exact same numerical eigenvalue, this layered system ensures they aggregate correctly into the final characteristic polynomial. The count and word chains share an absolute spectral radius, but that heavy binomial multiplicity of n choose L on the word chain requires an entirely new asymptotic trace analysis to resolve. That analysis targets a specific mixing observable, the stationary weighted average of conditional point start chi-square distances. This diagram illustrates the exact stationary average identity trace formula. The binomial mass pushes the total sum upward, while the eigenvalue to the power of 2t pulls it downward. The transition hinges entirely on this tension, the upward explosion versus downward power law decay. This dynamic is governed by fixed parameters, specifically where alpha and beta are greater than 0, and the constant c falls strictly between 0 and the minimum of alpha and beta. To measure the power law decay, the analysis calculates the absolute moments, defining q sub L as the expectation of the absolute value of u minus v to the power of L. The proof evaluates both the positive and negative endpoints separately to establish tight, rigorous bounds on these moments. The strength of that decay relies entirely on two explicit exponents, 2c and alpha plus beta minus 2c. The trace formula strategically sums only over the even eigenvalues. This ensures their absolute moments equal the actual eigenvalues, avoiding any mathematical cancellation in the lower bound. Calculating those exact absolute moments and preventing lower bound cancellation creates the rigorous conditions necessary for the specific n over log n threshold to emerge. This graph plots where tension breaks, marking a sharp threshold at log 2 over 2 delta times n over log n. Above it, the trace collapses to 0, bounded by a sublinear split. Below, it diverges to infinity, exploding at a central even degree. If we reduce the parameters alpha and beta back to 1, the constant simplifies to log 2 over 2, recovering the classical diaconus Lin constant. Moving to the epistemic weight of the claims, this graphic shows the strict verification status of the preprint. It remains an anonymous, unrefereed candidate. The reproducibility package contains 3,177 explicit verifier predicates, checking matrix traces, absolute radius identities, and finite exact kernels. This expansive suite provides strong producer-side falsification support, checking for formula translation errors and finite exactness. It cannot, however, mathematically prove the endpoint asymptotic. No part of this theorem has been formalized in a proof assistant, and the specific behavior at the exact critical constant remains an open question. The highest value next step is an independent mathematical reconstruction of the latent beta diagonalization, or a complete formalization of the proof in software.